Okay, great. Okay, so hi. Good morning, everyone. So it's week 10. This week, we'll be talking about dynamic programming. I think dynamic programming is actually one of my favorite topics. There's something about dynamic programming that I just like. Okay, so okay, I've started recording. And so here's the table of contents for today. We'll talk a bit about the DP background, maybe a bit motivation, how to use DP, and then we'll go through the tutorial questions. Okay, so all right, a little bit background and motivation. Maybe I won't speak too much about it. Like I researched like why is it called dynamic programming? Some of you might be wondering, but the too long didn't read is like the guy who coined the word dynamic programming just thought dynamic programming sounded cool. Okay, Richard Bellman. Okay, you can have a read later. But why learn dynamic programming, right? Like you might be thinking like, oh, will this be useful at work, or whatever you're gonna do in the future? Well, the joke answer is that it helped my friend get into Google because he was going for interviews and his interview was Google was testing him on dynamic programming. Okay, and one of my students last semester actually also mentioned that he had an interview with this company called Citadel, and they asked him DP questions and he happened to have learned it from 3230. Like I think after the tutorial, like a week or two later, he learned that a week or two after he learned dynamic programming, he got assessed on it for interview. So maybe it'll be useful for your interviews, right? So but the serious answer is really that dynamic programming is this design paradigm to help improve solutions that run from exponential time down to polynomial time. And that's really a huge improvement. We get something from like 2 power something into like n power 2, for example, or n power 3. And it's really a good candidate for optimization problems because oftentimes in various problems, you're interested in to find the minimum or the maximum of something. Okay, here are some applications of dynamic programming, right? So recently I learned this query optimization dynamic programming in databases in CS3230. So some of you who are taking it might have heard, might have seen the algorithm as well. Okay, but this is just to give a few examples. Okay, there's this particular cool example called seam carving, right? It's a content-aware image resizing where if you try to like resize an image, you see that the castle doesn't get squeezed, like it gets rearranged accordingly, right? And I thought it was a really cool, one of the cool examples. And if you have taken CS4230 computer vision, you might have seen this example before. Okay, so there's a video by 3Blue 1 Brown, Grant Sanderson, and he talks a bit about the DP idea somewhere in this video, in case you're interested. Okay, but I won't go through for too long about that. Okay, so for those of you who just came in, just now was just a brief background and motivation, but the whole content starts now. All right, so using DP. So when to use DP exactly? It's when problems exhibit this optimal substructure. And what does that actually mean? Optimal substructure means that you have optimal solutions, right? You want optimal solutions. Optimal here means like maybe you want to find the maximum of something. Okay, and the maximum of something, it can be constructed from smaller versions of the problem. So you break it down into smaller sub-problems. Okay, break it down to smaller sub-problems, find the maximum of those smaller sub-problems, and do some form of merging in order to get the optimal solution for the initial problem that you started off. Okay, this is optimal substructure. And it's especially useful when you have overlapping sub-problems. Okay, and I think the very typical example people use to explain dynamic programming is the Fibonacci sequence, where typically in Fibonacci, you have to recompute certain values of the Fibonacci number. But if you store it somewhere, then it'll be fine. Okay, you can just keep reusing the sub-problem to solve the bigger problem. Okay, so like over here, you can imagine that this node on the bottom left is the sub-problem, and a lot of the previous nodes in the higher levels actually use this node. And if you store this somewhere, you can avoid recomputation. Okay, so this is when to use that DP. Oh, right. So this one, dependency is directed acyclic. And this is an important point in the sense that because you break down a problem into smaller sub-problems, you don't want a case where, for example here, T of A depends on T of D, but T of D depends on T of A. So there's a cycle in the dependency here. So when you're doing dynamic programming, you want to avoid this cycle at all costs. You need to ensure that the dependency, the way you define the sub-problems is directed acyclic. Okay, must not depend on the result itself. All right, so how exactly to dynamic programming? Okay, that doesn't sound grammatical, but never mind. So the idea is to brute force, but carefully. So I think this kind of thought process might not be talked about in lecture. This is like my own, at least from my experience and from watching various resources, I think like this is a nice way to look at dynamic programming. Personally, for me, you don't have to follow this as well, okay? But to me, like dynamic programming is like trying to brute force, but carefully. It sounds a bit contradictory, but we'll see later why I think this makes sense. Okay, so first of all, you want to identify the sub-problems. Okay, identify how you want to break down the problem. Okay, so to solve the current sub-problem, assume you have solved the smaller sub-problems. For those of you who came from CS1101S under Prof. Martin Hens, you might be familiar with this thought called wishful thinking. But the idea is that it's really, you have a smaller sub-problem, right? Smaller version of the sub-problems. Just assume that you have solved it. Okay, we are in the process of trying to solve it, but just assume you have solved that smaller sub-problem. And the tip here is to not unroll the recursion. And not unrolling the recursion here means that if you have broken down into the smaller sub-problem, don't break it down even further to even smaller sub-problems. Just stop at the next level, okay? Assume you can solve that. And then use that value to build up for the current sub-problem, okay? All right, so I implicitly mentioned it just now, but you try to relate the smaller sub-problem to the current sub-problem, okay? You have to guess how it's related, okay? For Fibonacci sequence, it's simple, right? It's given by the formula. The f of n minus 1 plus f of n minus 2 gives the current fn. But a lot of different problems out there, you don't really have the relation immediately. You have to think about how all these different sub-problems are related. Do you perhaps like take the maximum of everything? Okay, and take note, this might involve trying all the sub-problems. Okay, and we'll see that today. We'll see that today. All right. So in a sense, this is trying all the sub-problems is the brute force part of this brute force but carefully thought process that I want to convey. Okay, so your sub-problem, again, as we mentioned earlier, it might be reused. So we store it in a table. Okay, and the time complexity is really the time to compute all the sub-problems. So imagine, right, like let's say you have a table of results, right? This is maybe n by m, for example. So the total time is the individual, all of these cells, you add them up together, right? And that will be the total time, time complexity in a dynamic programming paradigm. Okay, typically, a lot of people will say like, oh, time to compute one cell. So one cell times number of cells. Most of the time, this works. Okay, but just be careful. Sometimes there are problems where the cell, right, they differ a lot. So sometimes you have to consider rows, like consider an entire row and then like add up all the rows. Okay, it's okay if that didn't make sense, but just keep this in mind. It's really the time to compute all the cells. Okay, sum up all the cells. All right. So okay, so that is a brief like overview of dynamic programming. We'll go into specific examples during this tutorial. Okay, but before that, any questions? Okay. Okay, I saw a question in Archipelago, actually, like, is dynamic programming similar to divide and conquer? Personally, yeah, I think so. It's quite similar to divide and conquer in the sense that you try to divide into many sub-problems, just that typically in divide and conquer, the problems are not overlapping. Okay, so they are not overlapping. So dynamic programming just adds on an extra like measure to have this sub-problem stored in a table, the result stored in a table, so that you can reduce it. Yeah, so in a sense, I think it's similar to divide and conquer, except that you have to be careful about the analysis as well, because in divide and conquer, the problems do not overlap. So you can express it in recurrence, and typically it's fine. You can use master theorem and solve it normally, but with dynamic programming, it's slightly different, the analysis. You have to compute the time to calculate all the sub-problems, all the individual cells. Okay, if there are no questions, let me go on to the first question. Okay, so first question, I just want to take note, if you have seen the tutorial used counterclockwise for the points. It arranged like P1, P2, P3, P4 in a counterclockwise fashion, but for this set of slides, when I was designing it, I unintentionally used clockwise. So just keep that in mind. Okay, but without loss of generality, it should work either way. All right. So here, right, the first question talks about this thing called convex polygon. Okay, so don't be scared. It looks like we have pictures, but let's try to go through it slowly. So a polygon is represented by points like P1, P2, all the way to Pn stored in an array. Okay, and we'll deal with only convex polygon today. So convex polygon here looks something like this, and there are classes where there are non-convex polygons, like for example these diagrams. So just keep in mind, like we only deal with convex polygon today. Okay. We can define a notion of like a sub-array, like a sub-polygon in this fashion. So the sub-array Pi all the way to Pk is polygon consisting of Pi, Pi plus 1, Pi plus 2, all the way to Pk over here. Okay, sorry about that. So Pi all the way to Pk. Okay, so this is the representation. Okay, no need to care too much about like how actually it is implemented in like a computer machine. Just abstractly imagine like you have points, some data structure to represent a point, and then the points are stored in an array in this fashion. Okay, so that's a convex polygon. Now, triangulation of convex polygon is you take 3 points, for example, Pi, Pj, and Pk, right? And then let's assume there's this function, right, called the weight of the triangle. What is this? What is it exactly? What the weight exactly is? You can define a lot of different functions for it. I'll talk about it slightly soon. But so for example here, Pi, Pj, Pk forms this triangle, and the weight Wij, is the weight formed by this triangle. Okay, weight of the triangle formed by these points, sorry. And we assume that it's fast to compute this function. Okay, so the cost of triangulation of this polygon, right? So if you imagine creating triangles everywhere, like maximize all the possible triangles, leave no points behind. Notice how there are n-2 triangles, okay? So why n-2? You can imagine like you fix 2 points as anchors, like maybe you fix this point and this point. Now there are n-2 points to choose from for you to form a triangle. Roughly that's the intuition, but in case it doesn't like sink in yet, it's okay. Take some time to think about it later, but trust me for now that there are n-2 triangles formed by this polygon. Okay, so there are many possible triangulation. Just now was just one example, right? So there are n-2 triangles here, but there are different ways you can triangulate. So this is another example of triangulation. Okay, this is another example. And maybe like if you're still thinking like what is exactly the weight of the triangle, again, there are many different definitions of weight. A classic definition of a weight of a triangle is the length of the triangle edges. So in case you need a concrete definition to work with today, just imagine that the triangle, the total sum of the edges, the length of the edges, right, is the weight of the triangle form. Just imagine that for now, okay, if in case you really need the definition of weights. I tried to give a motivation last sem, but I think I'll skip that in the interest of time today. Okay, and maybe motivation-wise, like why are we interested in triangulation? I think those of you who learn computer graphics, I don't, okay, but maybe some of you who learn computer graphics, my friends told me that it's used to approximate smoothness of a surface. Okay, so maybe this is why we might be interested to learn about triangulations. Okay, so the first question, right, is about minimizing cost. Okay, so let's Cij, right? I think the tutorial uses like tau ij, but for now, for simplicity, I'll just use C for notation simplicity. The Cij is the cost of optimal triangulation of Pij. So consider some polygon, like let's say I and J is here, right? What is the optimal way of triangulating this polygon? Okay, we are interested in that Cij. Okay, sorry. Then we want to make use of this Cij to compute the optimal triangulation of the entire polygon. We want to find the triangulation with minimum cost of the entire polygon. Okay, and the first step we want to try to do for dynamic programming in general is to write down the recursive formula for the above problem. Okay, like how is the smaller versions related to the bigger problem? Okay, and remember, like why we are interested in this problem in the first place is because there are many different triangulations, right? Like this is one possible triangulation, this another possible triangulation, and they both give different costs. We want to find the one that gives us the best cost. Okay, so the best cost in the sense of the smallest cost. Okay, so the first question asks you to find the recursive formula. Okay, express Cij in terms of Ci prime J prime, where Ci prime J prime just represent a smaller polygon. Okay, so for example, right? For example, let's say I have C1n. C1n is what I'm interested in. Maybe I imagine it cutting into two. Like a possible way is to cut it into two, right? To cut into polygons, Ci K and Cki. So two polygons. One is Cik and Cki. Can I maybe relate what happens if I just separate into two polygons? And then maybe is it just like as simple as like adding them up? Does it give me the optimal answer for the entire polygon? Okay, this is here. No, take note. I'm not saying they are equal. I'm saying this is a question mark. Okay, this is a possibility, but there are many different ways you can try and break down the problem into smaller sub problems. This is just one example that I'm trying to convey. That might not be correct. Okay, so I would ask you to think about this. Like you can fill in archipelago, right, for question 1, but if you're confused, do let me know. I understand like maybe it's a bit abstract, right? Ask me to repeat. So please give me a thumbs up if you're okay with the definitions. If you want me to repeat, please let me know. Okay, because we'll be working with this question the entire tutorial today. So if you don't follow the first part, then chances are the later part will be a bit of a struggle as well. So can you just give me a thumbs up if it's okay? Okay, so few. Okay, a couple. Okay. So, okay, just think about it for a bit. Let's resume at around 11:20. Fill in archipelago if you manage to figure it out, but otherwise just say you don't know. It's fine, it's fine. I think this is the first time I saw this problem, I also had to think a lot. I don't think it was that easy to figure out. Okay. I hope that at least when you say you don't know in archipelago, at least you understand the question, like the definitions and what the polygon is, what each symbols represent. Okay, so it's okay if you cannot answer this question, but at least I want you to understand the notations. Mm-hmm. Okay, so yeah, okay, so some guesses are in archipelago, okay, and most don't know. I think that's fine. Okay, let's go on. As long as you understand the question. And again, I want to recall this paradigm I showed earlier, right? So it's about brute forcing, but try to do a careful brute force. What you want to do is identify the sub problems, figure out, assume that you have solved the smaller sub problems and try to relate it to the current problem at hand. Okay, and typically it's attempting to guess this relation that's quite difficult. Okay, so identifying the sub problems is already difficult, and guessing the relation is another like step in the difficulty. Okay, so and again I will mention that this might involve trying all the sub problems, and we'll see that very soon. All right, so first step, identifying the sub problem. The question was actually nice enough to give you the how sub problem should be formulated. Right? So it says Cij is the cost of optimal triangulation of this polygon. There are many ways you can imagine like how to form the sub problems for other kind of like questions. Okay, for this question, we'll focus on this subproblem where Cij represents the cost of optimal triangulation of Pij. Okay, then again, to solve the current subproblem, assume we know that some values we can obtain, right? Can we use it to compute the current subproblem? The example I gave earlier was like, maybe I have Cik and Cki. Let's say, just assume it's 10 and 30. Can I use 10 and 30 in order to compute C1n, the entire thing? Is it enough to cover all the possibilities, basically? Okay, so maybe it's 10 plus 3, at 10 plus 30, maybe it's 10 times 30, maybe it's minimum of 10 and 30. Like, what is exactly the relation? That is the problem that we try to cover. So here, right, which subproblems are appropriate for this problem? I want you to take note, we must cover all the possible triangulation, okay? Because the idea is that we want to find the minimum over all the possible triangulation. So the way we break down the subproblems must cover all the possible triangulation, okay? So the first step, right, you make a guess, like just guess something, guess how they should be related. So maybe my guess here, and which eventually will turn out to be the correct guess, okay, is guessing where the triangle with side P1, Pn should be, okay? So to triangulate this entire polygon, you need to triangulate this something with base this one, right? With base this one, but where should it go? It could be here. It could be here. This could be the first triangle with base P1, Pn, right? Or it could be here. It could be here, or it could be here. Okay, it could be here. Okay, this could be the triangle that gives optimal triangulation, or this could also be the triangle that gives optimal triangulation. Okay, I hope you're trying to, you can start seeing like the attempt to try all the subproblems here, where there are many possible triangles. This is example 1, example 2, example 3, example 4, but one of it must be part of the optimal triangle. Okay, we don't know which one of it must be. Okay, so recurrence for one triangle, let's not go too hasty. Let's say, right, I chose this triangle. I chose Pi, Pk, Pj, right? The recurrence for this one triangle is take the weight of this one, right? Take the weight of this one. This is this one, right? And then recurse on the two halves, the two other halves. So at the current level, you guess where the triangle might be. Let's say this was your guess. This triangle was your guess. You take the weight and then sum it up with the optimal cost of the two other polygons. Because take note, like when you take one triangle like that, the left half and the right half, it might not end up being a triangle. It still is a polygon, like a general polygon. So you need to recursively, right, assume that you can solve this left half and the right half. Okay, and the optimal cost just for this choice of triangle is this value. Okay, but then remember, our goal, right, is to ask which triangle to use, right? Because we want the optimal cost of all the possible triangulation. This was just the optimal cost in case your first choice of triangle was this one. But which triangle to use? Because there are many possible first triangles. Okay, there are many possible first triangles. You don't know which one to use, so try them all. Okay, and this is where, like I say, like brute force, but carefully. The brute force is because we are trying to guess everything. It could be this is the answer, this is the answer, the other triangle is the answer. So we try them all. Okay, so this was the relation for a single triangle, right? What you do is you iterate over all the triangles. This IKJ is just saying over all the triangles, okay? Then take the minimum. Take the minimum over all the triangles, over all the choices of the first triangles. Okay? So I want to pause here. Like, does this make sense? Like, anyone needs me to repeat? Like, can you give me a thumbs up if you're following the argument? And if not, please ask me to repeat, because we'll see this again and again. Okay, great. So thumbs up. Okay, that's great. Yeah, and in a sense, like someone in Archipelago asked, like maybe something to do with selecting all possible subsets. In a sense, almost, right? Selecting all possible subsets is really the very, very brute forcey. This one is like you guess what is the, in a sense, it's like guessing the first element and then recursing on the remaining. Okay, so great. So people gave me thumbs up, no questions so far. So this is the relation. In the good case where you recurse, there are certain cases, for example, right? If your polygon, right, is just a line like this, right? It's possible that when you recurse, it becomes like this line. In a sense, this is the base case, right? If it's just a line like this, then the cost just returns 0. So this is like base case. Base case. This is the recursive case. So in case like it forms a line just like that, just return Cij. But otherwise, if j is greater than I plus 1, it forms like at least a triangle, or maybe it's a like a fourgon, a quadrilateral. Okay, so all right, so this is the solution for question 1, really. Like this is the sub problems, right? So let's see, do I have time? I'll just quickly mention, right? When I was preparing for this tutorial last semester, I tried to think like, hey, is it possible to break it down into like different choices? So here's like some alternatives you can think about is, for example, a strategy is to choose an anchor point, right? And draw a dividing line. Okay, so just in case, instead of drawing a triangle, instead of drawing a triangle, then maybe you instead just cut it into two. Just cut it into two and then like cut it into two in this fashion. So the first choice is cutting into for this polygon. The second choice is cutting into two for this one and this one. Okay, let me use another color. So another choice might be if you cut it like this, then take the minimum over everything. Okay, try them all and find the smallest. Like this is a way I can break down the problem, but does it give the best answer? Okay, so something to think about. Maybe I'll skip it in the interest of time, but I gave several examples in the slides to try and see different possibilities. Okay, but I don't want to like confuse you too much now. So again, let me just recall, just to ensure we're on the same page. The recurrence for the question that we are interested in for today is choose the first triangle, okay, and try all the possible first triangles. Okay, there are other alternatives where some of them work and some of them don't. Okay, so lesson learned again. We try to brute force, but carefully. Okay, sorry about the disconnection. Okay, let me just quickly rush to continue. Okay, so all right. So I think like thanks to those who replied in the chat, like class group. So I think I left off right before like I showed a lot of the triangles. So I think I'll just skip all this. Just this slide is really just saying like, oh, there are possible other alternatives, right? But some of them work, some of them don't. Okay, so the lesson learned is really just we want to try brute forcing, but carefully, okay? And there are different possible ways to divide the sub-problem, and some are more efficient than the other. Okay, we need to ensure all the possibilities are accounted for, because in the examples where it fails earlier, right, they actually don't account for certain possibilities. Just quickly mention that in the next topic, I think this week's lecture, greedy algorithms, there is like a way that you don't need to account for all possibilities. Okay, but you need extra work to prove that they work. Okay, so just wanted to ensure that I'm not speaking muted. I think I'm unmuted. So just thumbs up if you can hear me, and I'll just keep going on in the interest of time. So the next question, right, is to fill it is this compute cost. So now that we have identified the recurrence relation, okay, we want to find out like, wait, what's the running time of this algorithm? Like here, we literally implement what we had in the previous slide. The question one shows this recurrence relation. Okay, so where you take the minimum over all the possible values, over all the possible choices of the first triangles. Okay, so you'd want to take the better result. Okay, take the best result for everything. Okay, and what's the running time of this? Is it exponential or is it quadratic? So maybe like while I try to figure out if my Wi-Fi is back up, just think about it. It's just multiple choice in Archipelago, so just make a guess. Let me try. If I disconnect again, that means my Wi-Fi is not back up. Okay, so just now you couldn't hear me. Okay, that means my Wi-Fi is not back up. But now that, okay, now can. Okay, yeah, I tried my Wi-Fi again and it didn't work. Okay, so right. So I think let's just go on. Okay, we have wasted some time. So I think a couple of you, so there's a bit of a mix, right? Most of you still thinks it's exponential while the rest thinks not. Okay, so actually it looks innocent, right? This recurrence looks pretty innocent, but it's actually exponential time. And the idea is because later on we'll see that they actually repeat the computation. So all right, so some definition to simplify. Let's say the algorithm compute cost from 1 to n, right, involves endpoints, right? It involves endpoints, so I simplify to say Tn. If it involves endpoints, I'm going to say it's Tn, okay? And the base case, if it only involves 2 points, it's a constant, okay? So this is the recurrence, okay? Remember, we are trying all the triangles, right? So we are. So for example, this first one here is trying to say, oh, let me guess this triangle, right? This is T2, and the other remaining half is Tn minus 1. Okay, so the second recurrence over here, second row, is doing T3, is choosing this as a first triangle, okay? And this recurs on this other halves, okay? Let me use another color. It recurses on this other parts. So this is T3, and this is Tn minus 2. Okay, so this Tn is really expressing the fact that we are brute forcing carefully over all the possible first triangles. Okay, so you can imagine like this is rotating, right? The triangle rotates. So eventually you at some point there's symmetry. So there's symmetry. So you see Tn minus 1 plus T2 again. Okay. By the way, if at any point you stop hearing me, just PM me on Telegram. Okay, I use 4G for my Telegram, so it's fine. Okay, so this is the recurrence. Tn equals to all this messy mess. Okay, so the trick here, right, is to notice that every smaller recurrence occurs twice. Like in this manner, right, T2 goes down and T2 goes up, like from top to bottom, T2 Tn minus 1, this goes down, and this one is in the other direction. It occurs twice. So I can simplify it in this way. Twice of summation of Ti from I equals to 2 to n minus 1. Okay, so this is the recurrence, the compacted version. And note here, this is On. Like this is something like On, because there are n minus 2 things. Okay, so this is from the previous slide. Here I'm going to do something interesting. Like a trick to do is you consider Tn minus 1 instead. Okay, so you consider Tn minus 1, and then you do a subtraction. Okay, and how does this visually look like? It's visually, this looks like imagine T1 plus T2 plus T3. Imagine this is the top one, and the bottom one is like T1 plus T2. This is the bottom one, right? If you do a subtraction, it's gonna cancel off. The common terms are gonna cancel off, leaving behind a single term. This is like a trick that we do to simplify if you have a summation of recurrences. Okay, so you are left with this single term, and that's what this 2Tn minus 1 here is. Okay, so in case it's not immediately obvious what this subtraction does, just look at this one on top. The one on top has more terms, right? And the one below, you take away the common terms. You take away the common terms by considering a smaller recurrence, Tn minus 1. So you get this recurrence relation, okay? And then bringing it over to the other side, you get something like Tn equals to 3Tn minus 1 plus C. And we hope you can solve this by now, and you should know that this is something like exponential time, okay? So it's okay if you don't fully get the math behind everything. This is just to convince you that, like there is a way for us to use the recurrence relation and eventually show that it's gonna run in exponential time. So we want to do better, okay? We want to do better. All right, so that's question 2. Any questions before I go on? Why is it not erasing? Just quick check, I'm still audible, right? Okay, great. I see the thumbs up. Okay, I'm gonna stop sharing and reshare because I think the Zoom froze. Oh, maybe I'll go to the next question first. Okay, so the next question, right, is to consider this algorithm, and we want to study some properties about it. Okay, so we consider, does this algorithm, does it compute 2 power n different sub-problems? Or how many sub-problems does it compute, right? Okay, so take a look at the options real quick, and let me share. Take a look at the options real quick. I won't use archipelago anymore because I think quickly disconnects everything. So just take a look at the options. Let me know if you don't understand any of the options. But the idea of this question is to figure out like how many sub-problems are being computed, and are they computed multiple times? Or like what's the time it takes to compute them? Okay. Okay, so all right. So I'm gonna go on, okay? And so I think last semester I remember the contention was whether like it takes exponential sub-problems, because the previous question says it runs in exponential time. So it might suggest maybe they're exponential sub-problems. Or is it like just n squared? So the answer is just they computes n squared different sub-problems. Okay, but each sub-problem is computed multiple times. Okay, I'm gonna try and convince with a small example, right? So T1n is the compute cost of 1n. Okay, so I represent it in this way. T1n. So for example, if I have T14, what does this mean? Let's say I have a rectangle, like a rectangle, right? So 1, 2, 3, 4. Then this half over here, right, is the recurrence where you choose this as the triangle, as the first triangle. That's why it's T12, right? This is T12 and T24. Okay, that's the left part. And the other part is if you choose this triangle, this is k equals to 3. If you choose this other triangle, if you choose k equals to 3. And this is the corresponding to this sub-problem plus this sub-problem. Plus this sub-problem, T34. Okay, so this is the first level. Okay, and furthermore, if you try to unroll this T24 some more, like this is one of the few cases like I think I'm okay with unrolling, so to convince you that it really has multiple sub-problems being used all over again. The 2-4 triangle, so it corresponds to this polygon over here. For you to recurse on this, the only choice of triangle is that triangle itself. It's this this triangle itself. Oh, wait. It's this triangle itself, and it has to recurse on T23 and T34. Okay, so what I've been just doing, in case it was confusing, is just trying to trace an example. What happens if you try to recurse on a rectangle, right? Like with the algorithm. And I want to convince you that really it shows that the same sub-problems is being computed multiple times. So indeed, it's multiple sub-problem computed multiple times. If you didn't understand the diagrams, think about it later. But the point is multiple sub-problems, the same sub-problem is computed multiple times. And the total number of sub-problems is actually like n choose 2. But in case like you don't think too far about the n choose 2, just think of it as like this T1, this first parameter has n possible choices, and the other one has n possible choices. So the naive way of thinking about the number of sub-problems is really like it's n squared, because there are n possible ones for the start point, and there are n possible ones for the ending point. Okay, in reality, you need like, if it's Tij, it should be that okay, wait, let me think. Okay, never mind. Just keep it at that. So there are n possibilities for the left one and n possibilities for the right one. Okay, so that's why it's n squared different sub-problems. Okay. All right. So let me go on. Bottom-up triangulation. Okay. Sorry. Before I go on, like, does anyone have any questions? Okay. 10 minutes for the last question. Hopefully, you have enough time. Can you just give me a thumbs up if it's okay? Okay. It's reassuring. All right. Let me go on. Okay. So bottom-up triangulation. So just now, we formed the recurrence, right? In dynamic programming, there are two approaches. So we typically try to build from bottom up or from top down. So top down, typically we just use the recursion directly, where bottom up, we try to build up algorithms like progressively. Okay, so I'm not gonna waste time like trying to give too much time to solve this problem. Okay, but take note of the goal. So we want to define this, we want to complete the code such that the algorithm finds the value for Cij. Okay, so it finds the value for Cij of Cij correctly, and it runs in On cube time. So the time to compute the optimal triangulation is actually On cube. Okay, and we compute at most n squared different sub-problems, and that is same as our observation before, but each of them exactly once. Okay, meaning you want to save it somewhere so that you are able to reuse it. You don't have to recompute. Okay. So this is the question from bottom up. Okay. So I'm just going to go on with the question. The strategy that we want to employ, right, is if you have a cell, right, how can you compute that particular cell? So imagine you're storing the result in a table, right, in a 2D grid. Let's say I want the result of this cell. How do I compute it? Okay, which table should I relate it to? Should I relate it with like this 1 and 2? Okay, or maybe should I relate it with the entire 1, 2, 3, 4? Okay, so that is the purpose of figuring out the relation in the first place. And then take note, the ordering is also important. Okay, because we want to fill up in a certain order. Like for example, if I'm computing this cell over here, right, I want to ensure that all this 1, 2, 3, 4 that I use, they are already the correct value. Okay, so that's why the order is important. You want to fill up in the correct order, fill it up in the correct value, fill up the correct values in the correct order. So this is what you want to keep in mind when doing up bottom-up dynamic programming. Okay. For question 4, I want to start with the intuition of like how we worked out the bottom-up solution. Okay. The intuition here is that we start from a small polygon. Okay. So imagine I have a super huge polygon, right? Let's just forget about solving the large problem, right? Let's say we just care about solving this triangle first. Like what's the cost of solving this triangle? This smaller triangle, P1, P2, and Pn, for example. Then I care about solving the next triangle, P1, P2, Pn. Sorry, this is P3. Okay, so start from the small polygon, finish calculating all the small polygons first. Okay, and we increase the size of polygon over time. So once you are done with all the triangles, okay, try all the quadrilaterals. Okay, so try all the like P1, P2, P3, P4. Fill this up, okay? And how we solve for the quadrilateral is literally by guessing the first triangle, right? And then recursing on the rest. But because we have computed the smaller triangle, like let's say P2, P3, P4, we've computed this smaller triangle, right? This means that we are in the correct order, right? So we start from a small polygon and then start increasing in size. Okay, guess all the triangles for that polygon. And take note, right? When I say try all polygons of that size, it's really like, imagine the triangle. It doesn't have to base in P1 and Pn. Maybe you can imagine rotating a triangle around. Okay, so, okay, and be sure that it's gonna be fine. All right, so this is the intuition. Start from the small polygon, build it up over time. Okay. Let's take a quick breather. Hopefully the intuition is okay so far. For those who are okay, please give me thumbs up like usual, because I think it's very prone to being confusing. So visualizing the table, right? So this is 1 to n, right? 1 to n, 1 to n. They are 2D. Okay. So the base cases, right, is literally when it's a line, when it's a single line. Okay. So these are the base cases. Okay. So these are the base cases. And then our goal is this T1n over here. Remember, we want to compute the entire polygon. And this is starting from 1, ending at n. So this is 1, this is n. This is our goal. We want to find a way, starting from the base cases, to compute all the way up to the other corner. Okay? So how to compute a cell? Okay, this is what I said earlier. We should compute a cell. For this particular cell, take note, the recurrence here, T13, right? 1, 2, 3, is taking T12. It's like taking T12 plus T23, right? Plus the weight of this triangle. Okay, so it takes T12, 1, 2, 1, 2 plus T23. Okay, so sum this 2 up plus the weight, it gives you this cell. Okay, this is for this value. And then what about the other one, right? What about the other one? Let's say we are interested in this cell. How do you compute this cell? This cell, T14, is computed by using, first of all, there are 2 possible ways to triangulate, right? You choose this triangle as the first one, and that corresponds to this cell, and plus the weight. Okay, the other possibility is to compute this as the other triangle, Okay, and then recurse, this is 1, 2, 3. T1, 1, 2, 3 is this one. Okay, so if you're confused, what I'm just trying to do is to really like imagine this recurrence, this recurrence that we've been discussing whole day today, right? In terms of how it looks like in the cells. So this one will correspond to this one, and this one is needed as well. So we need these cells, okay, and add the bump. So this is the recurrence for a single cell. And this is where I have this changing the K in between is for, because changing the K in between is kind of like imagining how do I compute a particular cell. So this inner loop here is to compute the value for a particular cell. Okay, so this is the given a cell, how do you compute them? Okay, I'm running out of time, but all right. So this is what the changing all the K in between is for. And then right, another example, right? Let's say if you want to compute this cell, what you need is to compute these two things, compare it with these two things, right? Compare it with these two things, compare it with these two things. Okay, sorry, when I say compare it with these two things, I mean like after adding it up plus the weight. Okay, so by computing that value, T whatever plus T whatever plus the weight, you compare it with the next T whatever plus T whatever plus the weight. Okay, so this is really iterating through all possible K. Okay, so at this point, we know how to compute a cell. So the hard part is really over. Okay, so the next thing you have to figure out is in what order you should fill up the table. Okay, to fill up the table, notice how you need to traverse this diagonal down. Because the reason is because, like for example, when you compute this particular cell, right, you need to have filled up this guy and this guy, as well as this guy and this guy. So you need to fill the diagonal somehow. Okay, you need to fill the diagonal somehow. Okay, so one thing to note is that the j minus I is always different by a constant. For example, along this diagonal, 3 minus 1 is equals to 2, right? 3 minus 1 equals to 2, and 4 minus 2 is always equals to 2. It's different by a constant. Okay, so how you do it is that you increment for I to n minus size, right? So to down. But then for the value of j, right, you increment by some fixed constant. For in this case, our fixed constant is 2, right? This is the size. This is the size, which we'll iterate through later. Okay, so for I, this is the left point. To compute the diagonal, you add it by a fixed size. Okay, in this case, imagine the size is 2 to traverse this diagonal over here. Okay, so the final part, okay, the final part is now you know how to compute diagonal. How do I move along the diagonal? Like how do I move along the diagonal to compute in this manner? Okay, and to compute that, notice that the difference increases. For example, 3 minus 2 here, right? Like if you 3 minus 2, it's only 1. The difference is 1. And 4 minus 1, the difference is 2. Okay? No, this is, wait. I think I made a typo here. I have to fix this later. Okay, so but anyway, the difference between I and j increases along the diagonal, along different diagonal. So to do that, you increase for size equals to 2 to n minus 1, and this will directly correspond to j equals to I plus size. So I understand some of this might feel very like confusing, like the way I just described it in words. But again, if we start off from the intuition, if we don't try to view it based on the table, this is trying to start from a small polygon, like this is a line, right? This is the base cases. And then you increase the size of the polygon over time. Increase the size of the polygon over time. This over here tries all the possible polygons of that size. Okay, this will try all the polygons of that size. And then this is guessing all the triangles of that polygon. Okay, so won't have enough time to pause and think too much. So please visit the slide after this. Final thing I want to mention is the time complexity to compute all the cells. Okay, one cell takes ON. Okay, because the range of I to J can be at most n elements, can be up to n elements. Okay, and we have ON squared cells. We have like a table of ON squared. It's okay to overcount a bit. I know it's like only the upper half that we care about usually, but we have ON squared cells. So because one cell takes ON squared cells takes ON cube. Okay, takes ON cube, and this is the final time complexity of this iterative DP. Okay, so I think I will spare myself the shame of like asking, like, is it okay or not? But because I think I admit I went a bit fast, I might have been confusing. Please check the video again and ask me if you have any questions. Okay. Here's an alternative way to fill up the table in case you're curious, you don't like the diagonal. So you can fill up like horizontally from the bottom as well, but I won't talk about why it works. Try and convince yourself that it's fine. Okay, so I'm already over time, but I'm gonna end now. So you can also write a recursive version if you have a table and like save the value to avoid recomputation. Okay, so bottom-up versus top-down approach, typically there are a lot of difference in time complexity, but there could be some difference that I won't talk too much here. You can look at it in the slides. Okay, this discusses the other approach that I didn't cover today, but it's actually a slower version. Okay, you can think of it why. In case you're interested to try implementing, there's actually a LeetCode question for this, right? Minimum score triangulation of polygon. So in case like to test your understanding of this question, you can try and after like some break, try and go to LeetCode and submit a solution for this problem. Okay, so again, class is, let me share the slides first before I wrap up, because I think some of you have to go. Okay. All right, so that's the link. So just to recap again, to DP, right? You think of it as like, for me, I think of it as trying to brute force, but trying to do it carefully. And you do it by identifying the sub-problems, right? And then guessing the relation. Assume you can solve the small problems, and how do you relate it to the current problem at hand? And the thing that you have to take note is that it might involve a lot of sub-problems, potentially all of it, okay? And store it in a table, right? To make it more efficient to avoid recomputation. All right, so again, if you find it confusing, there are tons of resources, fortunately for dynamic programming. I've linked some of it here, okay? And some additional questions in case you want more practices. All right, so thanks a lot for today. Sorry for the hiccup with the Wi-Fi issues, okay? But let me know if several questions. I'll stay here to answer questions. Okay, so thanks a lot, guys. So sorry for the technical hiccup. Okay. Okay. All right. So I think I received a question in Archipelago. So I'll put it in the chat, but I'll read it out for the recording, right? So the question is, you need help decoding questions that use cost, accounting method, and potential method. Are there any tips to get the answer without guessing? So wait, maybe I'll just put it on, like, I'll delete it later, but for the purpose of showing it to the video. So sharing screen, right? Right, so this is the question. Decoding questions that use cost. Are there any tips to get answer without guessing? You can follow the tutorial, but when attempting the assignment questions, you were very lost. So I think I'm not very clear what you mean, like decoding questions that use cost. Like, is it like figuring out what the cost is or some other things? Figuring out what the cost is. Okay, so this question is based on amortization. Maybe let's see. Are there any tips to get the answer without guessing? I think typically guessing is the first thing I would do, right? Guessing the cost. But second of all, I think more importantly is for me to study like the behavior of the operations, right? So for example, in the tutorial last week, we have an example with a queue. Like with a queue and you push in. You push in, right? So like a way I might not guess about it is to think about for that particular operation, must something have happened before that operation happens? So for example, during NQ, if you during NQ, we have no guarantees about what happens before all these possible NQs, right? There are a lot of possibilities. We can have multiple NQs, we can have multiple DQs and so on. But what you know is that when you call DQ, when you DQ something, right? An NQ must have happened. So an NQ must have happened. So in a sense, like, because an NQ must have happened, the way I think about it is that, can I shift some of the cost? Can I distribute some of the cost over from the DQ over to that particular NQ? So that's why in the tutorial, NQ has a higher cost. It has maybe like, I think cost 2, if I'm not wrong, instead of cost 1, because you want to shift the cost a bit, shift the burden a bit to NQ. Okay, shift the burden a bit to NQ so that DQ becomes cheap. Okay, so I can't exactly remember what the assignment questions are, but maybe let me open up the assignment now. 1 second, yeah. Like question 2. Okay, sure. Let me look at the assignment. Assignment 7, right? Okay, let me share screen again. So the assignment 7 question, right? Sure. Like I think you're right that this you're asking about what about the instance no data structure algo we know is given. But question 2, if you think about it, okay, so here, right, variant of the binary increment problem where the cost of flipping IF bit. So I think again, well, I agree this is there's no data structure explicitly, but if you think about it, like in terms of like incrementing the values, right, like from 0, 0, let me see, 0, 0, 0 to 0, 0, 1 to 0, 0, 1, 0 to whatever, right? So let me think. For this problem, once you flip the IF bit, like from 1, you possibly know how many increments must have happened. So let me see. Oh, okay. So again, like I think how I will try to study this is like, for example, if I have 0, 0, 0, okay, 0, 0, how about question mark? 0, 0 question mark, right? And let's say this flips to 1. This becomes 0, 1, 0, 0. Okay, so again, I'll try to think about when this expensive operation happens, like 2 power I, for example, 2 power I, it costs 2 power I in this question. What must be the previous state, right? What must have happened? What's the previous state? So the previous state must be that this question mark must all be 1. Must all be 1. So can I like associate some value like 1 over to this like can I associate some value over to these 2 1s before flipping this 1? Okay, I think that's the approach for the classic binary increment problem in lecture. Okay, for if we use counting method and potential method, but I think for this question might not be immediately straightforward, right? The answer, because how do you ensure like the 2 power I is accounted for when you are doing like how do you pay for this 2 power I? So maybe I'll have to think about further about how to solve this in the accounting method or potential method variation. But at the very least, I think when I saw this problem the first time, my intuition really tells me to try the aggregate method, the method that we didn't try in lecture. Okay, sorry, that we didn't cover in tutorial. So try the aggregate method because the lecture actually has the aggregate method for this question, and I think like it's a slight extension, a modification of the aggregate method in lecture. So if you're asking about how to solve this problem in the accounting method and potential method fashion, maybe I'll have to get back to you a bit later, right? But at the very least, I think to me, seems like aggregate method is one way you can more straightforwardly adapt this problem from lecture. Do you have other like, does that somewhat like clarify a bit about thinking about this the state of the question, you know, like what happens when the expensive operation is done? Okay, so in case you're curious about accounting method or potential method for this question, I can give it a bit of thought. Okay, but at the very least, using aggregate method is okay, you're lost to how to think about this accounting. Sure, let me try and see how I can get there. The answer is like, as we know, yeah, the lecture said the aggregate is less accurate. You're right. Less accurate in the sense that like I feel like typically aggregate is just less flexible if you have many different kind of operation, right? It's less flexible. So accounting typically is more general. It allows like variations in the way you account for different costs. And like maybe if I were to draw an analogy, right? For this question too, it's okay to aggregate method in my opinion, because all you do is single operation. You're just increment. This structure only has increment by one, increment by one, increment by one, increment by one. Okay. Whereas in the tutorial question, we have very variation of operations. For example, like adding to the queue or removing from the queue or deleting multiple things from the queue. There are like 3 or 4 operations, and different operations might have different costs. So in a sense, like using aggregate method is only reliable. No, I won't claim to say only reliable, but at the very least, it's reliable when you only have one operation, right? Because you are sure that the sequence of operation is always increment, 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 right? For the tutorial question, there could be a lot of like possible combinations. You could NQ then DQ. You could NQ then NQ. You could NQ then add multiple things and then DQ and then NQ, right? The point is like for tutorial, you don't have like a surefire way of like figuring out the cost, because the sequence of operation literally has like many possibilities out there. Whereas in this question, aggregate method is at least a good candidate still, because the operation is fixed. You are sure that the sequence of operation is always increment, 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 increment. So you are sure the what do you need to plus something, plus something, plus something. Does that like help like explain a bit more about aggregate and accounting method? Yeah. Yeah. Okay, great. Yep, sure. Okay, so the question is, when we have more than one operation, it's better to use the other two methods. In my opinion, yes. In my opinion, yes. Because well, sometimes there's just a lot of things going on, right? Like I won't say like method fits all. Based on my experience, when we have more than one operation, typically we use the other methods. Yes. At the very least, it's not clear to me how you use aggregate to reliably guarantee like what the sequence of operations should be. There might be a way, but as you said, maybe it's better to use the other two methods. But again, don't fixate yourself. Like if it's not working out, try and fall back and see if you can get something working. Okay, nothing is really fixed out there. Yep, no problem. Do you have any other questions? Okay, sure thing, sure thing. Yeah, I'll try my best to try as well, and maybe I can like advise you, or if you have attempted, you can ask me to see if it makes sense. No problem. Yeah. See ya. Okay. Okay. So all right. So by right, tutorial is over. Like no one else is in the room, but I think like I'll just cover some of the things that I had in my slides that I think like it's worth talking about. So alternatives to so earlier recall that so this no one is in the room right now. I'm just recording just because why not, right? Like just get it into the video. So the question one idea is really to choose the first triangle, and I want to explore different alternatives that might work or might not work. Okay, so the first alternative I propose is you choose this anchor point. Like let's say you anchor based on this point over here, based on this point, and then you draw a dividing line, and then find the cost of both polygons and then sum it up. Okay, so the full strategy is based on this anchor point. You divide them all. You divide them all and find the smallest. Find the smallest like sum of the cost of both polygons. Okay, so for example, like this is one way, right? This is one way. Maybe another way. Sorry, the polygon is bad. Maybe another way is like to draw it like this and recurse on both sides and then add them up. Okay, so try for all anchor, starting from this anchor point, try out all the dividing lines and then recurse and then add them up. Okay, so the approach is whether, the question is whether this is a correct approach or not. All right, so the answer is no, it is not covering all. The thing is, it doesn't cover all triangulations. Like a simple counter example is like this square over here, right? If you choose this as anchor, there's only one triangulation that can happen, which is this diagonal triangulation, right? This single triangulation, and you are not accounting for this triangulation at all, because notice how this is the anchor point, right? You cannot cover this triangle. And what if this was the one that has the minimum cost? Maybe this is cost like 100, and this one has like cost of 5. Okay, this one has cost of 5. Then because of your choice of anchor point, right? Then you miss out on all the values. Or yeah, you miss out on certain values, not all the values. Okay, an alternative 2, right? Again, you choose an anchor point and draw a dividing line. But instead of like drawing it like that, what I do is I rotate clockwise. So for example, this is the first one, right? And then you move this point over here, and you move this point over here, right? Then again, you move this point over here, and move this point over here, and this another dividing line. Okay, so try them all and find the smallest. Based on this approach, right? Rotating clockwise, it seems to cover more things, right? It seems to cover more triangles. So the question is like, does it cover enough triangles? Okay, so I'll give you like 5 seconds if you're watching the video to figure out. Think of a counter example, pause this video. Okay, counter example, or like prove that it's correct. So the answer is no, right? It does not cover method again. So last time when I tried this approach, I think I tried up to pentagon and it seems fine. But if for example I have 6, if I have 6 a hexagon like this, right? Like a hexagon, this is the anchor point. The 3 triangulation or 3 dividing line, sorry, is this line, this horizontal line, and this particular line. And notice how like this is the only way you divide the polygons, right? And it doesn't cover the case where this is the triangulation. Okay, because none of these red lines ever fall into one of these things. Okay, it never falls into any of these things. Okay, so this approach also doesn't work. Okay, because it fails for larger values to cover some triangles. And because, again, what if this one is best? right? What if this is the best answer, right? Then we are missing out on this value, okay? And notice how like the alternative is, the both alternatives fails because you choose like an anchor point, right? But what if the anchor point is like all the points in a triangle? Basically, try all the dividing line. Divide like that, divide like that, divide like that also, divide like that also. And if you draw all the dividing lines, it's gonna end up like a huge mess like this. Okay, so does this strategy work? Okay, does this strategy work? And indeed it does, right? If you think about it, in a sense, this is brute forcing all the possible first cuts. Okay, brute forcing all the possible first cuts, but this is very inefficient. And I'll try to go through it right after this. But this is essentially really try all the possibilities, try all the sub problems, and this alternative really shows like how if okay, I'll talk about that later. But you really brute force all the possible lines, right? But again, like as you have seen in the earlier just now, it's better if you consider the first triangle only based on a certain base. Okay, so all right, so why is it inefficient? Okay, so if you think about it, this other strategy, so recall the running time of the better algorithm, the better working algorithm is O(n) cubed. Why? Because one particular cell, right? It takes O(n) to compute it, right? It takes O(n) to compute the value, and then there are O(n) squared cells that you care about. Okay, there are O(n) squared cells that you care about because you fix what's on the left, there are n possibilities. What's on the right, there are n possibilities. Tij, there are n by n possibilities, so it's O(n) squared. But the other alternative where you try, right, for one cell, the strategy to find the best answer for a particular polygon, right? Remember, one cell computes the best answer for this polygon. And how you do it is by trying all the possible cuts. Okay, you try all the possible cuts, and there are n squared of such possible cuts. Okay, because it's the same argument, because to choose a dividing line, you need to fix one point, right? And there are n possibilities. And the other one also has n possibilities, or n minus 1 possibilities rather. N1 minus 1 possibilities, because you cannot choose itself anymore, right? You try all this dividing line and then you recurse, right? So there are n squared possible cuts, O(n) squared possible cuts to compute just one cell. Okay, it's no longer like computing this and this. So this plus this versus like this guy plus this guy. Okay. Okay, it's no longer that anymore. It's really trying many cuts. Okay, I don't want to like illustrate this in the table, but think about it. To compute one cell, you need O(n) squared O(n) squared time to try all the possible cuts. And then same as before, you have O(n) squared cells. Okay, but now each cell takes O(n) squared time. Okay, so in total you have O(n) power 4 time in order to compute the entire table. And that's the time complexity of this other strategy. So the key lesson that I want to impart from this example is that there are multiple solutions to dynamic programming, right? So depending on your choice of recursion, it might end up differently. You might end up with different correct answers, but they have different time complexities. Okay, so it's important to like think like, oh, is it possible to improve? Okay, like sure, you're brute forcing, but is it better? Is there a way to brute force like a bit better in a sense? All right, so yeah, so I think that really concludes everything that I want to say for this tutorial. Yeah, all right, so I'll stop sharing and stop recording. I hope the recording ends up fine because I got disconnected in the middle. All right, thanks for watching.